Welcome to this explainer. Today, we're going to basically boot up the system architecture of our entire world. We're diving deep into the highly sophisticated science of cartography. And look, forget those dusty paper atlases you might remember from grade school. Today, we're exploring maps as incredibly complex, dynamic information systems.
So let's kick things off with a pretty crucial question. How completely lost would we be without this essential digital translation engine? Seriously, think about your daily life for a second. Ordering a package, checking the radar for rain, or just navigating to that new coffee shop downtown. Almost everything we do relies on some form of spatial data. Without maps, we wouldn't just physically lose our way. Our entire modern infrastructure, I'm talking logistics, urban planning, environmental science, the whole shebang would literally break down.
Because, let's face it, reality is overwhelmingly complex. Our physical world is just incredibly dense with an infinite amount of data points, from the bottom of the Mariana Trench to the top of Mount Everest. But maps allow us to downsample this massive chaotic data set of reality into a beautiful, highly readable interface. They filter the noise so our human brains can actually process what's going on.
To understand exactly how this magic happens, we're going to run a quick system diagnostics check. Our agenda today: reality's interface, the communication chain, modeling the world, and finally, the art of encoding. Let's get right into it.
First up, reality's interface.
The absolute crucial point here is that cartography isn't just about drawing pretty pictures of coastlines anymore. Modern cartography is literally the field that establishes a direct interface between the environment and us. It's this vital tool connecting the geospatial where with the thematic what and the temporal when. So a map doesn't just tell you where a city is located. It can tell you, what the noise pollution levels are and exactly when they hit their peak. It lets us ask super complex questions like, where were the most bank robberies happening between 1950 and 1960? And boom, you instantly see the answer visualized.
Think about the before and after of this interface. On one side, you've got the raw, just immense complexity of planet Earth. On the other, you have a streamlined digital map running right there on your phone. That little screen strips away billions of totally irrelevant data points. I mean, you don't need to know the soil composition or the exact height of every single oak tree when you're driving, right? It gives you exactly the targeted spatial data you need to just turn left onto the correct street. It's basically the ultimate complexity reduction tool.
Moving on to part 2, the communication chain.
It is so fascinating to think about how maps actually talk to us. We can borrow from the famous Shannon-Weaver model, which was developed way back in the 1940s for telephone networks, because cartographic communication actually functions exactly like telecommunications. It's all about conveying graphical signals through a defined channel. The environment is captured, it's turned into a map, and then that map transmits data straight to the human mind.
In this high-tech network, the map author acts as the sender. They're transmitting an encoded signal. They take reality and encrypt it into lines, colors, and symbols. Meanwhile, you, the map user, you act as the receiver, decoding that signal on the other end. So if you look at a squiggly blue line and instantly understand, that's a river, well, a successful data transmission has just occurred.
But here's the catch, and this is perfectly captured by Kalachny's extended model. For this transmission to actually work, both the sender and the receiver have to be relying on a shared cartographic language. If the author encrypts a major highway as a thick red line, but you decode a thick red line as a political border, the communication totally fails. The map only works because we share an implicit understanding of these visual codes.
But here's where it gets really modern, and honestly, pretty cool. Today, we see this traditional chain completely collapse into what we call the prosumer. Think about the last time you opened an interactive web map. You probably compiled your own layers, right? Maybe you overlaid live traffic data, some restaurant ratings, your saved spots. You are generating the map and consuming it at the exact same time. The author and the user have merged into a single entity. A real game changer.
Okay, section 3, modeling the world. So creating a map isn't just a one-and-done process. The engine actually operates in 3 sequential filtering stages. We have primary data storage, secondary cartographic editing, and finally, tertiary cognitive perception. Every single step pushes the data through a tighter and tighter filter.
Let's trace that data flow really quick. In the primary stage, we acquire the raw data from the environment, say from a satellite survey, and we store it as a digital landscape model, or DLM. Then in the secondary stage, we take that massive database and apply cartographic rules to it to generate a digital cartographic model, or DCM. This is where the map actually gets designed. And finally, the tertiary stage is where it gets beamed into human memory, creating what we call a cognitive map right inside your head.
The absolutely crucial takeaway here is that this entire pipeline is inherently lossy. Kind of like compressing a giant audio file or saving a JPEG, cartography intentionally strips away unnecessary details. The technical term for this is generalization. Actually, imagine if we didn't do this. If we tried to map reality on a one-to-one scale with every single detail included, the final spatial interface would be a cluttered, completely unreadable mess. We literally have to lose data to gain clarity.
And that brings us to our final section, the art of encoding.
To encrypt reality, cartographers use a very specific visual toolkit. They start with the most basic graphical elements you can imagine, simple points, lines, and areas. But by applying design variables, things like shape, color, and size, they transform those basics into highly readable map symbols, dynamic data charts, and rich map graphics. It's taking cold, raw data and giving it a highly optimized visual form.
And we, the users, decode this visual form through a fascinating field called cartosemiotics. Now I know, that sounds incredibly futuristic and academic, but it just breaks down into 3 simple layers. First is cartosyntax, which is just the rules for forming signs, how we physically arrange lines and colors. Next is cartosemantics, which gives those signs meaning, like associating a blue blob with a body of water. And finally, cartopragmatics. This looks at the actual effect those signs have on the user. Does it successfully guide you to your destination, or did you just accidentally drive your car into a lake because you misread the blue shape?
So as we wrap up this explainer, we can see that maps are so much more than just paper and ink. They are complex communication networks carefully modeled and expertly encoded to interface directly with human cognition. I want to leave you with this final, kind of provocative thought. Since that final tertiary modeling stage happens entirely inside your mind, your brain is actually the ultimate rendering engine. So the next time you open a map app on your phone, ask yourself, how will your brain's cognitive map decode your reality today?